A very good evening, good afternoon, and good morning to all. I, Dr. Pallavi Saxena, welcomes you all, and Dr. Samina welcomes you all on the occasion of our sixth talk in iLEAPS Global Colloquium Series 2022. So iLEAPS is Integrated Land and Atmosphere Interactions, which is a global research project of Future Earth. And iLEAPS provides understanding of how interacting physical, chemical, and biological processes transport and transform energy and matter through the land-atmosphere interface. So the prime purpose of this colloquium is to introduce the scientific society people with the distinguished and significant work of eminent scientists all over the world. So it is a very bright opportunity for early careers, especially, to interact with the distinguished speakers and establish the bridge between the ideas and knowledge through this platform. So our today's speaker is Our today's speaker is Professor Jian who is in Department of Chemistry and the Division of Environment and Sustainability at the Hong Kong University of Science and Technology. Her main research interests include the development of analytical methods for airborne organic compounds, atmospheric chemistry of various chemical compounds, and chemical characterization of ambient aerosols for source apportionment and health effect studies. Her laboratory frequently provides analytical work services for the PM 2.5 monitoring network in Hong Kong. So she is currently a co-editor-in-chief of the General Atmospheric Environment elsewhere. She is a distinguished alumna of the Department of Environmental Sciences and Engineering at the University of North Carolina, US, and was elected a fellow of the Asian Aerosol Research Assembly in 2022. So today she will be speaking on abundance and sources of nitrogenous organic aerosols. And in this talk, she will describe about that how her team together has developed a method in creating an instrument that is capable of quantifying the organic nitrogen in aerosol samples. And she will not only provide the environmental impacts of the organic aerosols and the source apportionment also, but their origin and how they behave. So now I would like to again welcome Professor Jian to enlighten us about her work. So Professor Jian, the floor is all yours.
Thank you, Pallavi. Okay. Good afternoon or good evening, depending on where you are. It's really my honor to be able to speak to this seminar, and I want to thank the organizer, thanks Pallavi, for giving me these opportunities. So I'll take this opportunity to share with you some of our recent research regarding aerosol nitrogen, because considering iLEAPS is about to understand the interaction between atmosphere and ecosystem. So I feel probably nitrogen might be something we commonly are interested in. So everybody is aware of this nitrogen cycle, and we all know nitrogen is critically important. So it's important, fundamental to quantify the magnitude of the various nitrogen pools and also the fluxes between environmental compartments. For this talk, allow me to focus on nitrogen in the atmosphere. So if we zoom on to the nitrogen in the atmosphere, of course, nitrogen molecule is the most abundant species in the atmosphere, but this one is largely inert. Then after nitrogen molecule, we have nitrogen species present in the gaseous phase, such as ammonia, NOx, urea, small amines. We also have nitrogen gas, we also have nitrogen species in the aerosol phase. Then if we look at the aerosol phase, we have two major forms of nitrogens. One is inorganic nitrogen species, the other is organic nitrogen species. Today, I will focus on the organic nitrogen species and share with you some newly developed instrument we have developed in our group. So if we look at what's in the what kind of chemicals are in the particles in the atmosphere, let me show you this pie chart, which is like a textbook viewing of the major chemical species of fine particulate matters. As here you can see, we have organic matter, we have nitrate, we have sulfate, we have ammonia as major species. Then if we look at those containing nitrogen, we have these three forms: ammonia, ion, nitrate ion. Then the last one is organic nitrogen, which consists of many individual organic compounds. And previous studies of the organic matter part mainly focus on the carbon, rarely use nitrogen as a focal point. And if we look at the different chemical forms of nitrogen, the relative abundance of those inorganic versus organic ones is still largely unknown, simply because the measurement on the organic part is quite sparse. So we can identify some clear knowledge gaps. The first one is we don't know too much about those nitrogen-containing organic compounds and what's the quantity, what's the total quantity, and what are the individual quantities. And also, the second gap is the relative abundance of these two broad categories of nitrogen is still largely unknown. So if we zoom onto the organic part and look at the worldwide measurements using aerosol mass spectrometry, what here you can see is the organic aerosol part represents a significant part of aerosol mass and depends on locations. The range could be from 18% to 78%. When we think about the organic, then this organic aerosol constituent elements not only contain carbon, we also have other elements like hydrogen, oxygen, nitrogen, sulfur, and phosphorus. So today I want to call your attention to nitrogen. Let me create a new abbreviation, nitrogenous organic aerosols. I abbreviate it as OAN. First, actually, the interest on the nitrogenous organic aerosol actually has been there for a long time for a number of reasons. Here, I list 5 major reasons. The first reason is because nitrogen as a nutrient is important for ecosystem. So people have studied nitrogen compounds due to the link with the ecosystem. The second one is lots of nitrogen organic compounds. Actually, they are toxic. So this type of heterogeneous cyclic molecules, many of them are carcinogenic. Then then we also know many of the nitrogen-containing compounds, such as nitroaromatic compounds, they have a color, so they are part of brown carbon. Brown carbon is closely linked with how aerosols modulate the global climate. Then we also know some secondary organic aerosol or constituents made of functional groups containing nitrogen, such as organic nitrates. Lastly, we also know some nitrogen compounds, especially amine compounds. They are very active molecules in leading to new particle formation in the atmosphere. So we have various reasons to study those nitrogen molecules. And then if we look at the chemical forms, in terms of measurement, the inorganic nitrogen species, mainly ammonia and nitrate, their analytical chemistry is well established. The most typical analytical approach is to use ion chromatography to measure their abundance. Ion chromatography is typically sensitive enough to quantify those concentrations present in the atmosphere. In comparison, when we look at organic nitrogen, the analytical method is not that well established. Since there is really no direct method to measure the organic nitrogen, so the most commonly organic nitrogen is measured as the difference of the total nitrogen minus those inorganic nitrogen form. And I also wanted to call your attention is when you think about it, organic nitrogens, there are actually two pools of organic nitrogen. One is water-soluble one. The other is water-insoluble one. So existing techniques are able to handle water solution. So water-soluble one can be analytically assessed, but the water-insoluble one, due to its insoluble nature, right now there is really no good way to analytically measure them. So if you look at the literature, zooming onto the organic nitrogen part, mostly they are talking about the water-soluble one. So the figure on the right shows proportions of dissolved organic and inorganic nitrogen in rainwater or bulk deposition over the globe. So roughly, if we look at the dissolved organic nitrogen out of the total nitrogen, the proportion is 30%. What this number tells us is organic nitrogen appears to be a very important pool of nitrogen in the atmosphere, but they are rarely sparsely measured. So we have this need to get good measurement, and in order to get good measurement, first we need to have good analytical tools. Okay, so little bit of summary of the current status of bulk aerosol nitrogen measurements. We are looking at the total nitrogen pool, and it consists of organic nitrogen and inorganic nitrogen. Then if you look at under organic nitrogen, we have water-insoluble one and water-soluble one. And for inorganic nitrogen, we have ammonia and nitrate. As I said earlier, the two major chemical species of inorganic nitrogen, their analytical methods are already established. For organic part, because there is no good method, so different method has been resolved. Then when we look at this organic nitrogen or the total nitrogen pool in the aerosols, there was a very small number of measurement and using the elemental analyzer. But the analyzer is really poorly suited in giving in quantifies the trace level of nitrogen in aerosol samples. We can appreciate this if we think about it. Aerosol collected on filters, on one entire filters, often has less than 1 milligram per filter samples. But for elemental analyzer, typically the detection limit is already quite close to 1 milligram. So using elemental analyzer, it's very difficult to get a low concentration level of organic nitrogen. Because of the lack of direct method, so this organic nitrogen part is obtained indirectly by doing subtraction. For analytical chemists, we know whenever you deal with subtraction method, difference method, you sometimes you would get a negative concentration. Simply, the two quantities you use to do the subtraction might have comparable measurement uncertainty. So as a result, you would get mathematically you would get a negative concentration, but physically we understand negative concentrations really do not give us any meaning. So this really is something very annoying, and indeed, because of this, we feel really urgent that we need a direct method to get aerosol organic nitrogen. Then another problem with the existing aerosol nitrogen measurement is what the insoluble part was impossible to measure. Simply, we couldn't extract it out using solvent. Then, as a result, we wouldn't be able to use, for example, total organic carbon analyzer with nitrogen options to measure what insoluble organic nitrogen. I wanted to emphasize the importance of address this deficiency, the drawback with the different method. Here I copied one sentence, actually two sentences from the paper by Professor Sarah Cornell from University of Bristol. In this review paper, she said, an important issue in all organic nitrogen data sets, given that organic nitrogen is necessarily determined as a difference between total nitrogen and inorganic nitrogen, is the occasional incidence of negative values for the difference. Published reports of organic nitrogen data therefore need to report both total and inorganic nitrogen, so that the negative values can be dealt with systematically and transparently. So we can see that this problem has persistent, the negative concentration problem inherent with difference method has persistent for a long time. And in the past more than decades, people, scientists almost give up to address this issue. So what I'm going to present is we now develop an instrument that allows we directly report organic nitrogen concentration. First, I still wanted to say a little bit about the general abundance of organic nitrogen molecule in aerosols. So, the organic nitrogen molecules are actually really numerous and have extreme chemical diversity. In the past 1 decade or so, the application of ultra high resolution mass spec in environmental field, in the atmospheric science field, that has allowed us to have unprecedented knowledge about the molecular level information. So here, this slide shows in the literature, shows chemical formulas identified in both ambient samples and source samples. If we focus on those formulas containing organic nitrogen, we can see in the aerosols we have formulas that contains C, carbon, hydrogen, nitrogen, such as chemicals like amine, imidazole. We also have molecules containing carbon, hydrogen, oxygen, and nitrogen, examples such as amino acids. We also have organonitrate, which can also fall in this CHON group. Then in addition, we also have some compounds that contains both nitrogen and sulfur. So typically, they are nitroxyl organosulfate. So here we can see the type of organic nitrogen molecules could be quite diverse. From compounds containing reduced nitrogen functional group, such as amine, to compounds containing oxidized nitrogen functional group, such as organonitrate. The second information message I would like to call out is, if you look at these pie charts are all obtained from mass spectral data, and these mass spectrometric data, they are not entirely quantitative, but nevertheless, the intensity tells us something semi-quantitatively. The importance of those broad groups of compounds. As you can see the pies, so those nitrogen-containing compounds are really important. Although the information is not quantitative yet. Okay. Next, I wanted to introduce the instrument we have recently developed. So the top shows the simplified schematic diagram of our instrument. Our instrument basically consists of an oven where we put 1 square centimeter of filter punch from filter samples inside the oven. Then this oven is temperature programmed up to all the way to 800 Celsius degree. So materials on the filter can be thermally evolved and then enters this back oven where there is manganese dioxide at a high temperature of 870. So any gases, species coming out from the filters would be oxidized, and the carbon element would be oxidized as CO2, and the nitrogen would be oxidized to become NOY, various nitrogen oxide species. Then the flow come to the detection boxes and split into 2 flows. One flow goes to carbon detection, and one way of detecting carbon is to convert all the CO2 into methane through a methonator, and then the methane can be quantified using FID, or directly the CO2 can be quantified using NDIR. The second stream goes to a nitrogen detection box. Here, first, this stream will go through this molybdenum converter, where the NOY would be reduced to nitrogen monoxide, and then nitrogen monoxide is detected by the chemiluminescence instrument. Actually, in our case, we simply use a commercial chemiluminescence NOx analyzer. So the key feature in this instrument is because we are using thermal evolution, so all forms of nitrogen, regardless water solubility, can be thermally evolved and then be detected. For our instrument, we have 2 detectors, one for carbon and one for nitrogen. And the carbon signal would help us to differentiate inorganic nitrogen and organic nitrogen, simply because for nitrogen signals, if it doesn't accompany any carbon signals, then that has to be inorganic nitrogen. Then one more feature is we then use nitrogen and carbon thermal fractions and processes as thermal fractions using a statistical tool called multivariate curve resolution. And that allows us to resolve inorganic nitrogen and organic nitrogen. So the instrument, this instrument has been already published in EST. So if you wanted to know more details, please check out our paper. Then one very important feature with these analyzers is greatly improved detection limit. So our nitrogen analyzer right now is able to go down to 0.1 microgram nitrogen per sample. And this is about 7 times lower than that is achievable by elemental analyzer for nitrogen detector, which is around 0.7 microgram nitrogen per sample. So this improvement of 7 times sensitivity is very important to capture most of to deal with most of ambient samples. So second, what's mentioning feature is with this approach, we are able to get the water insoluble organic nitrogen molecules. So as such, this part of ON, which is previously not able to be quantified, we are able to get it and include as part of the total organic nitrogen in the aerosols. Then lastly, with this type of instrument, we can just directly process filters without doing any sample treatment. And this greatly reduces labor and time. As a result, we are able to process a large number of samples. And as everybody in the audience know, for environmental science, we really need to collect enough samples in order to make the data representative, also in order to understand how different the environment vary from one another. So basically data is the key and we need lots of data. So figure to the right simply shows this instrument has very good mass recovery for various of nitrogen species. We have tested lots of nitrogen containing compounds in organic nitrogen chemical species and various of organic nitrogen species, and that nitrogen exists in different functional group, nitro group, amine group, also incorporated in the aromatic rings. Next, I wanted to explain a little bit about how we actually separate inorganic nitrogen and organic nitrogen. Here, I show some example thermograms for a single standards. And the top one shows the temperature program. So for our analysis, we have set 6 temperature steps. 150, 180, 300, 400, 500, and 800 Celsius. Then next, if you look at the individual thermograms for single standards or some mixtures. For example, ammonia nitrate, it's quite volatile, so it mainly comes at the lowest temperature step 150. Then the other 2 common ammonia compounds, ammonia sulfate, ammonia bisulfate, they undergo decomposition at the lower temperature, but most of them would come out at the 2nd step and the 3rd step. What we do uniquely next is we actually extract some organic nitrogen from real-world ambient samples. So this mixture basically captures the complexity of the aerosol organic nitrogen mixture. So when we get this organic nitrogen mixture only is we basically use some solid phase extraction to get rid of to get rid of the inorganic nitrogen species, so it's inorganic salt. So here, what you see is actually some thermograms of complex real-world organic nitrogen mixture extracted from aerosol samples. Then we also tried what the insoluble one by washing the filter. So what is remaining is all or only what insoluble organic compounds. And here we can basically see for the real-world organic nitrogen mixtures, most of them come out at the temperature steps 300 Celsius and higher. So if you taking this information as a whole, then basically we can see inorganic nitrogen and organic nitrogen, they have distinct thermal features. Also, they do not, their peaks overlap, but their thermal features are distinct enough. So this problem, this type of problem, or we have peaks that are still overlap. It's common with chromatographic separation of complex mixture. And in the chromatographic separation of complex mixture, and this problem has been solved by using statistical tools. So we have taken the hint from that experience. So what we do is we basically use this multivariate curve resolution data treatment tools. Here, still simplified schematic diagrams, and we generate thermal, we call it thermograms. So what we get is at each temperature step, how much carbon, how much nitrogen we get. And this serves as the input data matrix. And then we can use MCR to separate this data matrix into two matrices. One is so-called factor matrix. The other is contribution of the factors. And these factors can be associated with either pure inorganic nitrogen compounds or pure organic nitrogen compounds. So by using this data tool, we are able to separate the nitrogen signal into inorganic ones and organic ones. Since this is not so traditional way of separate chemical species, so we have to verify this MCR tool actually is reliable. What we have done is we have prepared synthetic mixtures that consist of ammonia sulfate, ammonia nitrate, and hulis. Hulis basically only contains organic nitrogen, extracted from ambient samples and free of those ammonia ion and nitrate ions. Then we mix them using orthogonal experimental design. And here I show 36 mixed samples. So in these synthetic mixtures, we know exactly how much inorganic nitrogen we have in each sample and how much organic nitrogen we have in each sample. Then we generate the thermogram and go through the MCR data treatment, and then we get our inorganic nitrogen and organic nitrogen. So if we compare the our instrument derived inorganic nitrogen after MCR treatment versus those imported nitrogen, we see very good agreement. Similarly, for organic nitrogen, we also get a very excellent agreement. The slope is nearly unity, and the intercept is fairly small. So this is a result with synthetic mixture. How about the real samples? So what we do is we use a set of 60 ambient samples we collected at the urban site in Hong Kong. And again, we generate thermograms for nitrogen and for carbon, and then use MCR to do the data processing. So in the end, we basically derive the instrument tells us what is inorganic nitrogen in this 60 ambient data set. And those inorganic nitrogen species, including ammonia and nitrate, they can be accurately measured, quantified by ion chromatography. So that gives us an independent way to verify whether our instrument derived, or our new instrument derived inorganic nitrogen, whether it's comparable. And here I show you this figure to again demonstrate that this MCR2 actually is pretty robust in terms of separate inorganic nitrogen and organic nitrogen. Besides a laboratory version of the instrument, we actually have take one step further and built an online instrument. So most part of the online instrument is quite similar to the laboratory ones, but the difference is we here have one additional part which takes care of online sampling, and this is directly interface with the front oven. So for this instrument, we right now have already achieved a 2-hour time resolution. And with this online instrument and the 2-hour time resolution, that means we are able to monitor the diurnal variation of aerosol organic nitrogen. So diurnal variation is a very important dimension of information in terms of source identification and tracking. When you think about it, if we look at vehicle-derived sources, we know we would expect signals would be higher during traffic peak hours. So this type of diurnal information is extremely useful when we track atmospheric pollutants. So this is a photo of our online version. Actually, the instrument itself is quite simple. Here is the casing, the housing, the front oven, and the oven unit. And we have this one, the black one. It's the box detecting carbon, and here this is the box detecting nitrogen. And the online version of the instrument is described in detail in this paper published in Atmospheric Environment. Okay. So with the instrument that got developed, we now apply the instrument to do some real science. Since my group have been doing PM2.5 monitoring for a long time, so we have access to lots of archived samples, especially in our own region, which is Pearl River Delta. So for testing the instrument, the usefulness of the instrument purpose, altogether we have looked at more than 600 PM2.5 samples collected from 12 sites. And those 12 sites include Beijing, Qingdao, in the northern part of China, and the remaining part are concentrated in the Pearl River Delta in southern China, simply because Hong Kong is located in PRD, so it's much easier for us to have access to samples collected in this region. And for these 12 sampling sites, the range of atmospheric environment vary from rural site, urban site, and suburban sites. So later on, for the ease of discussion, we group the sites into 3 broad categories. And first, according to the type of sites in terms of urban influence. The other is we also separate geographically remote areas. For example, because two northern sites, we put them in this one, suburban and northern China plan, and for those sites located in the South China, then we further separate them in urban sites and for suburban and rural sites. Okay. So now here, let's look at the data. Here I show the abundance of inorganic nitrogen and organic nitrogen. The first column shows inorganic nitrogen abundance. So as the x-axis is concentration, and because y is simply frequency distribution, count of the number of samples. And the middle one shows the data for organic nitrogen, and the last column is the fraction of organic nitrogen out of total nitrogen. So let's look at the organic nitrogen abundance. If we look at the annual average, the organic nitrogen concentration across the 12 sites is from 0.4 to 1.4 microgram nitrogen per cubic meter. And so since we are only counting nitrogen alone, okay, and it depends on chemical species, then we can convert this into actually molecular mass. If we compare different sites, then we can see more PM 2.5 organic nitrogen were observed in the northern China. If you look at the last row, and compare with those sites in the South China. So basically, if you compare this distribution with the two on the top, so those in Beijing and Qingdao basically have a higher organic nitrogen. In a way, probably indicate that the northern part of China actually is more polluted than our Pearl River Delta. So looks like organic nitrogen might be linked with pollution extent. And then if we look at the relative importance of organic nitrogen, so we look at the percentage. It ranges from 17 to 31% across all sites. So here we can see ON is a significant part of aerosol total nitrogen. Then if we examine site-to-site differences, then we can see from urban to suburban rural site, we could see the relative importance of organic nitrogen would increase. So if you look at compare urban versus suburban rural in the same region in the PRD, apparently in the urban area, we would have a higher ONTN fraction. So here is a middle point. Most of the samples would be higher in the fractions than those samples collected in the rural or suburban areas. Here, I wanted to briefly show you some additional data. We use the online version of the instrument, and the measurements were made at the urban site in Shanghai. Again, the online instrument tells us the same result. ON makes a significant portion of total nitrogen in PM 2.5. Here I actually list also the gases nitrogen species. We have an environment with high NOx. And if we look at those nitrogen in the gases species, nitric acid and ammonia is quite high. Then if we look at the aerosol part of nitrogen, here we can see the aerosol is 0.41 microgram per nitrogen per cubic meter. So although it's small compared with the gases phase of nitrogen, but still this part is still quite important. Okay. So some statistics, if we look at the organic nitrogen in the out of the total aerosol nitrogen, we basically highest values so percentage could reach as high as 57. So during some episodic period when the condition is favorable for producing organic nitrogen, we actually could have roughly half of the total aerosol nitrogen as organic. Then next, I wanted to talk about sources of nitrogenous organic aerosols. So if you look at the whole atmosphere and then try to zoom onto those sources that are able to generate nitrogen-containing compounds, they fall into two groups. One is primary emission sources, such as biomass burning and also some primary biological particles. They would emit amino acids. So the second type is secondary processes involving chemical reactions in the atmosphere. Since we are talking about the nitrogen-containing molecules, and there are different ways to incorporate this nitrogen into aerosols. It's possible to utilize ammonia or utilize nitrogen oxide, or simply some organic nitrogen vapors. So that gives us a hint that there are multiple sources and the chemical formation pathways leading to the existence of organic nitrogen molecules in aerosols. So next, we tried to use the data to answer what are the major organic nitrous organic aerosol sources in the atmosphere using the filter data that we have analyzed. And so the way we do it is we use this widely used source apportionment tools called positive matrix factorization modeling. And I will not go into detail to explain what. Briefly speaking, it's basically we have a chemical composition matrix in many samples. And basically, we tried to resolve this mass balance equation to decompose this data matrix, chemical composition data matrix, into two separate matrix. One represents so-called source factors. The other represents factor contributions, factor strengths. Then we also have error matrix. And so way we solve this equation is we try to minimize this error matrix. So using these tools, we are able to identify a number of sources. I here use one example, which is based on chemical composition data from our urban site in Hong Kong. And the chemical composition coupled with PMF allows us to resolve 9 sources. The first one is industry emission, co-combustion. Second one, vehicle emission. Third, ship emission, biomass burning. And fifth is primary biological particles. And so next one, soil dust, sea salt, sulfate formation process, and the nitrate formation process. So if we investigate source by source, then we can see some sources are primary emission sources, some are secondary sources. Then here I wanted to use example as example to show you the source apportionment results of nitrous organic aerosol at 3 sites in 4 seasons. So 3 sites I picked is one is Jian in our urban Hong Kong, and this NS is a rural site in Guangdong province, and the last site is Beijing, which is a suburban location. I show you both annual average results and also seasonal results, and each pie basically proportional to the quantity of organic nitrogen. So here, a few messages we can get from this source apportionment results. Nitrous organic aerosols show significant spatial temporal heterogeneous. From one side to another, we can see difference. And if we look at different seasons, the difference is also quite distinct. Quite obvious. Then, if we look closely, then the common major OAN sources are biomass burning, primary sources, and secondary formation and primary biological aerosols. Then, if we take a closer look at the primary biological aerosols, this one actually is quite significant, accounting for 7 to 18%. And also, we notice if we look at urban sites versus non-urban sites, then those non-urban sites would actually have more coming from primary biological aerosols, which makes sense. Since in rural locations, probably we have more those fungi, this type of biogenic, primary biogenic aerosol particles. Although not shown in this chart, but I wanted to say vehicular emissions can be a significant source of nitrous organic aerosols at the urban side. For our urban Hong Kong, roughly, it could be 14% on an annual average basis. This one, I will simply quickly go through. For the online amendment, it allows us to examine the diurnal variation. So that information is useful, as I indicated earlier. If we look at our Shanghai monitoring data, we look at those periods with enhanced organic nitrogen concentration. What we found is we found at least there are 3 types of ON sources. The first one is associated with vehicular emissions, as represented by the first column. Basically, these enhanced organic nitrogen coincide with traffic peak hours. And then the second type we are able to identify through this type of diurnal variation analysis is in certain nights, we can see organic nitrogen enhancement, presumably as a result of NO3 radical chemistry, which NO3 radical reacts with organic chemicals, then forming organic nitrogen molecules. The last type is more closely related to daytime photochemical processes, because it's in sync with ozone peaks. So this is more related to photochemical formation processes. So here's my summary slide. From our recent work, basically, we are happy that we create a unique aerosol nitrogen analyzer, which enables sensitive and convenient quantification of OAN, nitrous organic aerosol. And because of its instrument method, it doesn't require any sample treatment. So that allows us to analyze hundreds of samples or even thousands of samples. The online version of the instrument can go one step further, allows us to monitor diurnal variations. And from what still I consider limited data set, we can see organic nitrogen makes up a significant portion of the total nitrogen in aerosols. So for this pool of nitrogen, we really cannot ignore. Then from what we have learned about the source analysis, we can see clearly a few major sources that contribute to nitrous organic aerosols. secondary formation is during night time or during daytime. And biomass burning emit nitrogen-containing organic aerosols. And of course, primary biological aerosols, they probably likely emit amino acids, this type of nitrogen-containing compounds. As I also hinted, other sources also contribute, such as vehicle emissions in urban sites. So with the detailed chemical composition, we actually can provide quite a detailed source analysis for a specific location. So the ending message is with this nice analytical tools, we really are seeking collaborations with those who are interested in looking at the exchange process between the atmosphere and the ecosystem. I stole this figure from the paper by folks et al. So if we think about the atmosphere, we really need to quantify both the organic part and the inorganic part, because if you compare these two pools of nitrogen, for most locations, they are quite comparable. And with our analytical tools, now we are able to have a much better handling in terms of quantitative numbers. This is really the last slide. I would like to thank the two group members, really instrumental in the work I presented today, Dr. Yu Xu and Dr. Li Jian. They developed the laboratory version and the online version, respectively. I also wanted to thank my collaborators all over China in contributing as filters and also some of the chemical analysis. Finally, funding support from Hong Kong Research Grants Council and also National Science Foundation of China, and also support from Shanghai.